This video is about conservation of momentum. So we've been going through impulse and momentum, and we've been focusing on what happens to a single object when it collides with something or gets hit by something. But with conservation of momentum, we're going to be looking at two movable objects and what happens when they collide. So conservation of momentum is all about collisions. So if you think about what's happening when we have two objects moving towards each other. So we have our two carts moving towards each other. And when they actually collide, due to Newton's third law, the forces they exert on each other are going to be equal in magnitude and opposite in direction. And the time of impact is also going to be equal because you can't have one touching the other for longer. So if the force and time are both the same, then that means the impulse on each object must also be the same. So down here, we have the impulses are the same. They're equal in magnitude and opposite in direction. So if the impulses are equal, then the changes in momentum must also be equal. And since we have mass, or change in momentum is mass times change in velocity, our mass times change in velocity are equal. Our velocity, of course, is final minus initial. And so I can distribute my mass and I get m1 times the mass of the first object times the final velocity of the first object minus the mass of the first object times the initial velocity of the first object. And then the same information for the final object, or sorry, for object 2. I can then rearrange the equation by moving my negatives to each side, and I end up with the sum of my initial momentums, the initial momentum of mass 1 plus the initial momentum of mass 2 is equal to the sum of my final momentums, mass 1 final, or final momentum of mass 1, final momentum of mass 2. So this is basically the law of conservation of momentum. Your initial momentum and final momentum must be equal after a collision. And so the law of conservation of momentum is going to be stated in the absence of an external force, and that's usually gravity or friction. The total momentum before the collision is equal to the total momentum after the collision. So for example, in this picture down here, if I calculate the total momentum of the truck before the collision and the total momentum of the car before the collision, and I add them together, I get 3,300 kilogram meters per second. If I do the same thing after the collision, I'm going to come up with the same total momentum. Now, when we solve problems with conservation of momentum, rather than using the long conservation of momentum equations, and these three down here are the basic equations. Each of these represents a different kind of collision. And if you want to use the equation, you would have to memorize all three of them or learn how to build them. So if we want to make problem solving a little bit easier, we often use something that we call the momentum box. And one of the things you have to remember about the momentum box is that only our momenta, that's the plural of momentum, go into the box. You never put mass, you never put velocity. We only put momentums in here. Now this is the basic structure of the box. Basically what you have is you have your initial momentum and your final momentum, whatever your object 1, object 2, and total. So we'll show you how to use this in just a moment. But as you're solving momentum, conservation of momentum problems, you really need to draw a before the collision picture and an after the collision picture and label the picture with what you know. So now we're going to go through the different kinds of collisions and show you how they affect the box or how you use the box to solve them. So the first kind of collision we're going to talk about is called an inelastic collision. It's where the objects stick together. If you notice the two astronauts, you start with two objects, two astronauts, and after the collision, they move off together. They are stuck together. So we have the same thing here with the car hitting the truck. Now the charts above give you the mass and the velocity of the car and the truck in the beginning, and it does also at the end. But we're going to go ahead and use the beginning information to try and solve for that final velocity. So the way we use the momentum box is we have to look at how many objects do we have in the beginning. Well, we start with 2 objects. So I'm going to make this box start with, whoops, 2 objects. So object 1 is going to be our car. Object 2 is going to be the truck. Now after the collision, we only have 1 object. So I just want 1 box. Now what I'm going to do is I'm going to put the momentums for the car and the truck in the box. So the car has a mass of 1,000 and a velocity of, 20. So the initial momentum of the car is 20,000 kilogram meters per second. You don't need to put units into the momentum box because everything's going to be the same. Now in the beginning, the truck has a velocity of 0. Well, mass times 0 is going to be 0. So the truck has no momentum in the beginning. Now I add my 2 momentums together and they will equal my total momentum. And since momentum is conserved, my momentum in the beginning is equal to my momentum at the end. So my combined momentum here is also going to be 20,000 kilogram meters per second. Once I have my momentum that I'm looking for, I'm going to take it out of the box, and then I can use that to calculate the final velocity. So momentum is mass times velocity, and my velocity is going to be my momentum divided by my mass. I have my momentum of 20,000 kilogram meters per second. But what is the mass of this car-truck combination? Well, it's going to be the sum of the mass of the car and the truck. So it's going to be the 1,000 kilograms of the car plus the 3,000 kilograms of the truck. So it's going to be 20,000 kilogram meters per second divided by 4,000 kilograms, and that's going to equal 5 meters per second, which is what the problem tells us after the collision. So let's look at another one where you don't have the picture to start with. So in this one, you have a 100 kilogram football player who's standing still, and a 70 kilogram football player running at 10 meters per second is going to collide with the first player. We want to know the final velocity of the 2 players after the collision. So I'm going to go ahead and draw a picture, and that should have been a straight line. But we have, let's make our first player who's standing still over here, and he has a mass of 100 kilograms, and his initial velocity is 0. So I'm going to say that this is our player 2. The other player is moving towards him at 10 meters per second and has a mass of 70 kilograms. So this is our before, and then after, they are going to be together moving away with a velocity that we don't know yet, and that's what we're looking for. But the mass of the 2 of them, our total mass, is going to be 170 kilograms. So now to solve the problem, I'm going to go to the box, and we start with 2 objects and end with 1. So the momentum of player 1 is 10 times 70, which is 700. Player 2 is not moving in the beginning, so he has no momentum. Adding them together, the total momentum of the system is 700. The total momentum of the combined group at the end is 700. And now I can take this out of the box and find my final velocity, which is going to be the momentum divided by that total mass, or 700 kilogram meters per second, divided by the mass of 170 kilograms. So the final velocity of this combined group is going to be 4.1 meters per second. So that's how you can use the box to solve a problem for an inelastic collision. The next type of collision is actually a reverse inelastic collision or an explosion. So when we have something like a cannon, or it could be a gun, you usually have recoil. So that means when you fire it, you can feel the gun blow back on you. And we can find the speed of that recoil using conservation of momentum. To do that, we treat our initial system as a single object, even though it would be the cannon with the cannonball. Even though they are separate, we treat them as if they're together to begin with, and then they're going to move in opposite directions after the explosion happens. So let's find the speed of the recoil of the gun after it's fired the bullet. So with this one, when we're looking at our box, this time we are starting with a single object and ending with two objects. In the beginning, we have a mass of 4 kilograms for the rifle, and we could add the 0.01 kilogram of the bullet, but right now the speed is 0. So the momentum of the entire system in the beginning is whatever the mass is times the speed of 0, which means the momentum is 0. Well, if the initial momentum is 0, the total momentum of is 0. And that means our final momentum is also going to have to be 0. So let's look at which piece we have enough information to actually solve for. Here's where we have the mass and the velocity. So my momentum of this group is going to be 0.01 kilograms times 300 meters per second, which is a momentum of 3. So I'm going to say, let's say the bullet is object 1 and the rifle is object 2. So that means our momentum here is 3. So 3 plus what equals 0? Well, that would be -3. So that means the momentum of the rifle has to be -3 kilogram meters per second. So I remove that from the momentum box. And my final velocity is my momentum divided by my mass. My -3 kilogram meters per second divided by my mass of 4 kilograms is -0.75 meters per second. So remember, the negative sign just tells you direction, so it just means that my velocity is in the opposite direction of the velocity of the bullet. So I would expect in this case to get a negative number. So we can also do this problem. We have somebody who's holding a ball and they're on ice skates, so we're essentially considering that it's frictionless. And we want to find the speed of the ice skater after they've thrown the ball. Well, in this one, again, we are starting with one object and ending with 2. Our initial momentum is 0 because they're standing still. So our total momentum is 0. So based on the information from the problem, the ball is moving with a speed of 5 meters per second. So we can calculate the momentum of the ball, which is 10 kilograms times 5 meters per second, or 50. So the ball, and the ball is 1, is 50. So that means her momentum must be -50. And again, we take this out of the box, and final velocity is equal to the momentum divided by the mass, which is -50 divided by the student's 50 kilograms, and that is a -1 meter per second. So that's how fast the ice skater would be going after she threw the ball. The last kind of collision is something called an elastic collision. This is where the objects do not stick together. So in this problem, if you look, the top is the before. So this one's at rest, this one's moving towards it, and the bottom is the after. So we start with 2 objects, we end with 2 objects. Here again, we start with 2 objects, we end with 2 objects. This next collision, we start with 2 objects, we end with 2 objects. In each case, you have 2 objects before and after the collision. So here we have our car and truck again, and this time when they collide, they bounce off of each other. So using the momentum box, we are going to have 2 objects both before and after the collision. So again, we're going to put our momentums in the momentum box. And the car again is starting with 20,000. The truck is starting with 0. And so our total momentum in the beginning is 20,000. Now for this problem, we do need a little bit more information. We need to know at least the final velocity of one of our objects. So in this case, we are looking for the velocity of the car. So if this is our car and this is the truck, we're looking for the velocity of the car. So we need to find the momentum of the truck. So after the collision, the truck has a velocity of 10 meters per second. That means the truck has a momentum of 10 times 3,000, which is 30,000 kilogram meters per second. So to find the momentum of the car, what plus 30,000 equals 20,000? Well, that's going to have to be negative 10,000. So now that we have the momentum of the car, again, I remove this from the box, and my final velocity is equal to my momentum, negative 10,000, divided by the mass of 1,000. And that means we have a final velocity of negative 10 meters per second. And looking at the answer up here, that is what we get. So that just means, of course, the car is moving in the opposite direction. So again, we can do a problem with the bumper cars. And we would have our bumper cars, and I'm just going to make circles because I don't draw. I'm going to call this one 1 and this one 2. Based on the problem, the first car in Ryder has a mass of 50 kilograms and is moving at a speed of 10 meters per second. The second one has a mass of 75 kilograms and is moving at a speed of 5 meters per second. And they are moving towards each other. Then they collide with each other, and they are going to be moving away from each other, and it tells us the second car bounces back, that would be the opposite direction, with a speed of 7 meters per second. So the question is, what is the velocity of the first car? So our momentum box gets made into 4 boxes, and we start with 50 times 10 is 500 for car 1. And then 75 times 5 for car 2, but notice it's moving in the opposite direction, so this is going to be negative 5. So 75 times negative 5 is negative 375. Add them together, and my total momentum is going to be 125. So that's going to equal my final momentum. So here, I know my final velocity, and so 7 times 75 is going to give me a final momentum of 525 for object 2. So what plus 525 equals 125? Well, that's going to be negative 400. So now I can remove this from the box, and my final velocity is my negative 400, sorry, it should have been down there, divided by my 50 kilograms. And that gives us a final velocity of negative 8 meters per second. So with these 3 different kinds of collisions, there is one specific difference that you need to know between an elastic collision and an inelastic collision. During an elastic collision, kinetic energy is conserved. If I calculate the kinetic energy of the system before the collision and the kinetic energy after the collision, they should be the same in order for a collision to be truly elastic. So in this case, the kinetic energy of the car, since the truck didn't have any, in the beginning was 200,000 joules. After the collision, the truck has a kinetic energy of 150,000 joules, the car has a kinetic energy of 50,000 joules, and when I add them together, they will also be 200,000 joules. Now remember, energy doesn't have a direction, so we don't worry about the fact that one's in the positive direction and one is negative. So we just add them together. And so these two are equal, which means that this is a truly elastic collision. So many of the collisions that we actually do, that we call elastic in problems, are not necessarily truly elastic. So if kinetic energy is not conserved, it is not a truly elastic collision. So if kinetic energy is not conserved, it is technically going to be an inelastic collision. The reason kinetic energy is not conserved in an inelastic collision is that some of the energy usually goes into deformation, whereas in a completely elastic collision, there is no like you wouldn't have a crumple zone or anything. It would be perfectly elastic as if they never really touched, which is why for a really truly perfectly elastic collision, you're probably talking about atoms coming near each other without touching. Electrons might collide with each other, protons, but most real things are not going to be truly elastic. So a quick summary, these are the three equations that you can use, or you can use the momentum box. And an elastic collision conserves kinetic energy. In an inelastic collision, kinetic energy is not conserved.